This is day 8, I think. Yes, it is. Okay, so day 8 looks like it's probability. Um, the circle graph below shows the number of each colored candy in the bag. So there's 8 blue in the bag, 9 yellow, 8 red, 10 orange, 11 brown, 4 green. Martin picks up a candy out of the bag, records the color, and returns the candy to the bag. He does this 20 times. How many times should Martin expect to pick an orange candy? Well, let's find out. So the first thing you would probably have to do is, or I would probably have to do is turn this thing on. Yeah, and I'm gonna add. So 8 plus 9, 8 plus 9 plus 8 plus 10 plus 11 plus 4 plus 11 plus 4. So too lazy to add this. Fine. So 16, 20, 30. Carry the 3. There's 50 candies in the bag. So if there's 50 candies, he wants to what? Pick up the orange. So the probability of picking an orange, and there are orange, 10 out of 50. So that's the probability of picking an orange, and if you'd like to change that to 1/5, that's fine. And to make our prediction, we're gonna multiply this by 20, right? So if we what do you call, take a candy from the bag 20 times and make, how many times would the orange come up? Well, 1/5 of the time, right? 1/5 times 20, and 1/5 times 20 is, we can simplify this, it's 4. So if you were to pick a candy, look at it, put it back in the bag, take another candy, look at it, put it back in the bag, and so forth. Obviously, this is with replacement. So out of the 20 times, you would expect him to get 4 oranges. 2, a spinning wheel is in a carnival is divided into 12 equal sections. Okay. I'll make this bigger. Players receive a prize if the wheel stops on a yellow, green, or blue. Yellow, green, or blue, and you are winners. So if the game is played 500 times, what would be the expected total value of the prizes given? So yellow, blue, or green. Okay, hang on a second. So yellow. So let's find out P of yellow, P of blue, P of green, and now I have P of blue here. So let's see what the probability of each is first. So the probability of getting blue is 1, there's only one blue. 1 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1 out of 12. Probability of getting yellow is 1, yellow, 2, 3 yellows. So 3 out of 12, 3 out of 12, or 1/4. And the probability of getting a green is 1, 2, 2 out of 12, or 1/6. So those are our probabilities, right? So now if you were to spin this 500 times, right? So let's say 1 out of 12. So we're going to use that and multiply by that by 500. Let me just read the question again. If the game is played 500 times, what would be the expected total value of the prizes given? Okay, so if you spin this 500 times, how many times would you expect it to land on blue? So we're going to use our probability, 1/12 times 500, and you can do that in your calculator. And we would expect it about 41.6 times, and we can't say 41.6 times, so 42 of those 500 would be, would be blue. Yellow, 1/4 of the time. So 500 divided by 4. So 125 times you would expect it to land on yellow. And green would be 1/6 of the times. 1/6 times, so again, I should rewrite this. 1/6 times 500. 1/6 times 500 is 83.33, or 84 times, right? Because you can't have 83.3 turns. So if it lands on on blue 42 times, you would expect to, every time it lands on blue, you have to pay $2. So you expect Carnival to pay $84. Every time it lands on yellow, you pay 80 cents. So times 80 cents. Carnival 125 times 0.8 would be $100. And then 84 times it would land on green, and green pays $1.30. So you actually wanted to land on green. So 84 times $1.30. By the end of the night, the carnival would have paid $109.20 in prizes. Okay. 3, Karen spun the spinner 50 times and recorded her results below. So right away we know this is experimental probability. The spinner had 5 number sections. Okay. Number 1 came out 13 times, the 2 8, the 3 10, the 4 12, and the 5 7. Based on these results, how many times should Karen expect to land on 3 or 4 if she spins the spinner 300 times? So the probability of landing on 3 or 4 based on her experiment. So he landed on 3 10 times and a 4 12 times. So I'm going to write P of 3 or 4 would be 22, right? 10 plus 12, 22 out of 50, because she did this 50 times. So in her experiment, she spun this 50 times and he landed on 3 or 4 22 times. Now, if she were to continue the experiment, right? She were to continue the experiment, and we're supposed to make a prediction, and so in her experiment, it was 22 out of 50 that landed on 3 or 4. So let's use that, multiply that by 300, and let's see what we would expect. So we would expect 22 over 50 times 300, which is clear 6, which is 132 times. So out of the next 300 spins, 132 times it would land on 3 or 4. So again, we're not using theoretical, we're using experimental probability. Okay. 4, the arrow on the spinner shown below will be spun 400 times. Okay, so can I make this smaller? No, too small. It's going to be spun 400 times based on the theoretical probability. Which graph best represents the number of spins in 400 times that the arrow will stop in each section? Well, so what we can do is that, so in blue, to make it fair, let's use the smallest denominator, the common denominator. Let's cut this everything in half, right? So now everything is in equal parts. So in blue, we have 3 sections. So how many sections do we have? 1, 2, 3, 4, 5, 6, 7, 8. So 8 sections are blue. So 8 sections, and out of the 8, 3 are blue. 3 8s are blue, right? It's blue, blue, blue. 1 out of them, 1 out of 8 is white. And 1, 2, 3, 4, 4 out of 8 is red. So the biggest one is red, right? So you expect it to land half of the time on red. So let's look at our choices. Right, so based on a theoretical probability, what would if we were to spin this 400 times, how many times would it land in blue, white, and red? So you know what, in order to stop guessing, so 4/8, this is theoretical probability, times 400 times, so half of the time. So 200 times would be on red. We're going to look in our graph and look for something that says 200 times will be on red. What is wrong here? Hang on a second. Oh, there is. Okay, 200 times will be on red, and 1/8 of the time. So again, we're going to multiply 1/8. 1/8 times 400, so it'd be 50 times. So on white, you expect it to land 50 times, and then the remaining one, obviously, is going to be 3/8. Times 400, which is 150. So we need to look for a graph here, a bar graph that shows that it's going to land on red 200 times. Well, obviously, right away, these two can go because we need to look for something that says red 200 times, and these two says red 50 times in this case and 50 times in this case. So this is gone, and this is gone. So let's look at the bottom 2 choices, and I'm going to erase this. So you can tell that the bottom C and D says that it's going to land on red 200 times. Actually, this one says it's going to land on red 200 times, on white 50, which is what we had here, and on blue 150, which is what we had here. So the only graph that matches is this one. Let me make it bigger now. The table below shows the results of a survey of 200 people attending a hockey game. So it's an actual experiment, again, experimental probability. So 200 people were asked. 68 said they're going to buy a cap, 19 a jersey, 22 a pennant, and 91 a program. This question sounds familiar. The attendance for the hockey game is about 25,000 people. Based on the table, how many people out of 25 should be expected to buy a pennant? So how many people bought a pennant? The experimental probability says that 22 out of 200 people bought a pennant, right? So if we take that and multiply it by how many people? 25,000, right? Because we used a little survey here. We surveyed 200 people, and out of 200 people, 22 said they were going to buy a pennant. So we can apply that, right, to 25,000 and see how the majority or the bigger population here would choose. So 25,000 times 22 divided by 50, so 11,000. That sounds wrong. So give me a second. 22 times 2, 3, enter, divided by 200. 2,700 people would be expected to buy a pennant, right? So you use the results of a survey to predict how the bigger population would behave. So answer is C. Pretty sure I gave you the question. 7, an ice cream shop conducted a survey of favorite milkshake flavors. So again, here is your, what do you call, survey. 17 people said banana, 25 chocolate, 11 strawberry, and 18 vanilla. Okay, so let's see how much that is, because it doesn't tell us. 17 plus 25 plus 11 plus 18 equals 71 people. So 71 people were surveyed, and these are the results: 12, 20, 21. Now, the ice cream is going to give away 240 people, 240 milkshake coupons, right? So they want to prepare and see how much banana, chocolate, strawberry, vanilla. So based on the survey, they want to see how the bigger population, in this case 240, is going to behave. So predict how many banana shakes the ice cream shop will give away. So in our survey, 17 people out of 71 said they liked banana milkshake. So let's take that and multiply by 240 to see how many of the 240 would actually like banana milkshake or order banana milkshake. So multiply that, and you're going to get 57.46 of a person. You can't have 57.46 of a person, which means 58 people out of the 240 would probably order the banana milkshake. 6, Raphael performed an experiment by spinning the arrow on the spinner 200 times. Here are the results. Okay, so there were only 3 colors, 3 choices on that spinner. If he's going to spin 20 more times, how many times would he expect to land on the red section? Well, based on the experiment, red was 105 over 200. Almost a little bit more than half landed on red. So if he spins this 20 more times, how many times should you expect it to land on red on the next 20? Well, let's multiply it by 20. And you're looking for something that's a little bit more than half. So 105, enter, divided by 200. You look, so 10.5. So again, closest answer is 10. So it's about 10 times in the next 20 spins you would expect it to land it on red. 8. At Marcy schools, a random sample of students were surveyed on their preference for school service in the cafeteria for food service. Each student gave only one response. Here are the results of your survey. How many people were surveyed? So let's add them up. So we always need the total. 56 plus 73 plus 22. And you get 151 kids were asked. Right? So Marcy has 1,200 students. Based on the data in the table, how many students are expected to prefer the traditional lunch line? So in the survey, 56 kids out of 151 say they want the traditional lunch line or prefer the traditional lunch line. So let's use that result and apply it to the bigger population to see how they would behave. So times 1,200. So in the survey, looks like about a third of them said they prefer the traditional lunch line. So it's going to be about a third. So 400 maybe the answer. So let's just find out. enter divided by 151. So it's about 445.03, but you can't have 0.3 of a person, or I'm going to make it 446 people out of the 1,200 students would also say traditional lunchtime, if, of course, that remains true. 9. For quality control, light bulb company conducted a random sampling of the light bulbs. The results are shown below. So they looked at light bulbs. Obviously, I'm pretty sure most companies, all the companies do that. And they took a sample of 100 light bulbs, right? 4 plus 96. So there were 100 light bulbs that they checked. 4 of them were defective, and 96 of them were okay. So if the light company makes 6,000 light bulbs in a day, how many can you expect them? How many defective ones, how many bad ones light bulbs can the company expect to make in a day? So the probability out of 100 was that 4 out of every 100 were bad light bulbs. For 4 out of every 100. So let's multiply by the total here, 6,000. So if you were to make 6,000, how many light bulbs, bad light bulbs, defective light bulbs would you expect? So again, about 240 light bulbs. So total, about 240 light bulbs you would expect to be defective. Big number. 10. Jose spun a spinner 50 times. The spinner landed on 27. The spinner landed on red 27, blue 9 times, and green 7 times, and yellow 7 times. What spinner is most likely to yield this result? So which of these A, B, C, D spinners are the ones that he spun to have these results? So one thing I know, so if I'm going to make a spinner, I know one thing, that that the green and the yellow are the same size. So the green and the yellow are the same size. So this one, check. And the red, compared to the blue, so the red should be 3 times bigger than the blue. Well, this red looks like, if I divide in 3, this looks 3 times bigger than the blue? Yes. So A sounds like it works. A so far looks like it works. B, let's just check on B. So again, green and yellow have to be the same. Well, they're not the same, so B's out. Green and yellow have to be the same, so C also is out. And then green and yellow in D are the same, but is red 3 times as big as blue? No, it's much more. It's too much. It's more than 3 times, right? Because the relationship is 3 to 1. And red is definitely more than 3 times as big as the blue. So we had the right answer on A. 11. So again, I need to make this smaller. The bar graph below shows the result spinning a spinner 1,000 times. The spinner has 5 colored sections. Which of the spinners most likely produced the above graph? And again, it's almost like the same one. So we're looking at a spinner that's going to have green, red, and orange should be the same size. Green, red, and orange. Green, red, and orange. Green, red, and orange. They're not the same size, so this is gone. Green, red, and orange are the same size. Blue. But blue should be a little bit bigger because it landed on blue, definitely a little bit more. So that's also gone. So you want something that has green, red, and yellow being the same size. Blue a little bit bigger. Green, red, and orange. So green, red, and orange. Are they about the same size? They look like the same size. Blue is a little bit bigger. And then yellow is the biggest. So this one looks like it's okay. Let me just check this one. This one is definitely wrong because all of them look like they're the same size, right? So we definitely have to see something where yellow, as you can tell, is the biggest chunk, and only in C that's shown. 12. Oh my God. Okay, Mary Beth has a bag of 25 colored beads. They were 5 different colors. 5 beads of each color. So there were 5 red, 5 blue, 5 yellow, 5 green, 5 purple. Mary Beth drew a bead from the bag and replaced it 30 times and recorded the results. So they're all in the bag, 5 of each color. You take one out, you put it back. So she did that 30 times. 6 of them came out red, 5 blue, 5 yellow, 7 times the green, and 7 times the purple. With what are the experimental theoretical probabilities that Mary Beth will draw a blue bead, is it bead? Bead when she tries again? Theoretical, so if you have 5 of each color, so let me put 5 here, 5, 5, 5, 5. Just by looking at the facts here, and there are 25 of them. So the probability of getting a blue is 5 out of 25, or 1/5, right? How did I write that? No, that's okay. The probability, you should have said the probability of getting a blue is 1 over 5. 5 over 25, or 1/5, right? And in the experiment, how many times did she do the experiment? She took a bead 30 times, right? Took one out, put it back in the bag, took another one out, put it back in the bag. She did that 30 times, and in her experiment, the blue came out 5 times. So I'm wondering, right, this is theoretical. And in her experiment, blue came out 5 out of 30 times, and 5 out of 30 is the same thing as 1/6. So let's see what the multiple choices are. The theoretical probability is 1/5. Good, check. The experimental probability is 1/6. Good, that's a check. The theoretical probability is 1 over 5. The experimental probability is 1/30. That's garbage. Theoretical probability is 1/6. No, it's not. It's 1/5. And the theoretical probability is 1/6. Again, garbage. So the only one that actually had the values that we came up with was letter A. All right, so theoretical probability of getting a blue, just by understanding the facts here, we knew that there were 5 of each color. 5 of them were blue out of 25. So 5 out of 25 is 1 out of 5. So that was the theoretical. On the experiment, when she actually did the experiment, how many came out blue? 5. But 5 out of what? Out of 30. Right? She did the experiment 30 times, and 5 out of 30 is 1/6. So the only one that matches is letter A. The spinner shown is used in the game. So each spinner, Esther, spins the spinner 8 times and get an even number 5 times. What statement correctly compares experimental and theoretical probability of getting an even number? Well, even numbers, 1, 2, 3, 4, there's 8. So the theoretical probability of getting an even number is 4 out of 8, or half. In her experiment, right, so that's the theoretical. In her experiment, what was the probability of getting an even? In her experiment, what does she say? She spun this 8 times, and how many times it came out even? 5. So 5 out of 8 in her experiment. And let me write, theoretically, you should have gotten 4 out of 8, or half. So let's look at our multiple choice. The experimental probability is the same as the theoretical probability. Not really. The experimental probability is greater than the theoretical probability by 1/8. That is true. The experimental probability is less. No, the experimental probability, you actually got more evens during your experiment, right? Because theoretically, only half of it should have been even, but you got more. But that's gone. This is gone. The experimental probability is greater than the theoretical probability by a half. No, it's not. So look. The probability of getting an even number was 4 of 8. That's the theoretical. In the experiment, she got 5 out of 8. So what was the difference? What's the difference between 5/8 and 4/8? The difference is 1/8. So correct answer is B. It 14. I think these are the last 2 questions. Quan spins the arrow on a spinner shown and records the results in the table. Okay, I need this a little bigger. I can't see. Okay, so she spun the spinner, and let's see how many times did she spin this. So let's add this up. So it looks like 21 and 29 is 50, 100 times. 100 times this was spun. What's the difference between the experimental and theoretical probability on landing on red? Well, landing on red, theoretically, when you just look at the facts, probability of landing on red, well, it's 1 out of 4. In her experiment, and I'll write experiment over here, in the experiment was 100 times, right? We're looking at red. 21 out of 100 times was landed on red. So what is the difference between those two? Well, the difference between the two, we would have to actually, subtract, right? So 1/4. So take your calculator. 1/4 minus 21 over 100. I'm finding the LCM, which is 100. 4 times what is 100? 4 times 25, right? So 4 times 25 is 100. So on top, 21 times 25 is 25. So if you subtract now 25 over 100 minus 21 over 100, the difference was 4 out of 100, and that's not in any of our answers. But if you simplify, 4 out of 100 becomes 1 out of 25, which makes our selection. Rachel flipped a coin 50 times and recorded the number of times it landed on tails. So the probability of landing on tails was 28 out of 50. Tails. In her experiment was 28 out of 50. Which results describes the reasonableness of this result? Well, in her experiment, 28 out of 50 were tails, but theoretically, the probability of landing on tails, right? What's the probability of landing on tails? 1/2. So if it's 1/2, and if you knowing that, and if you flip a coin 50 times, you would expect that it lands on tails 25 times. Did it land on tails 25 times? No, it landed on tails 28 times. So let's see what our multiple choices say. It is reasonable because 28 is close to half of 50. Well, yeah, she was expecting 25, but it came out 28, so that's okay. It's reasonable because there will be more tails than heads. That's not, right? There shouldn't be. There should have been 25 heads, 25 tails, theoretically. It is not reasonable because she will get 25 tails. No. It is not reasonable because she flipped a coin too many times. I have no idea what that means. So, correct answer, 8. And that makes this one done. So day 8 is done.